Notice in chapter 5 where primarily what we're doing is calculating support reactions. So if you look, this is table 5.1, support reactions, right? These are all the support reactions that you need to know, 10 of them. But the big three are what? What's the big three? Big, roller, big support. Pin does not allow any movement in the X, does not allow any movement in the Y, but does allow a rotation. Roller, just one force along the axis of the roller. And a fixed support, that means like a flagpole or beam embedded into the wall that restricts motion, the X motion, Y, and restricts rotation. So all three. There are a few others. Here they are. They're all right there. What you don't see is you do not see any distributed loads. That's because of equivalence. Equivalence says I can always reduce down to a single force, single moment. So sometimes you'll see a single force, single moment, single force, single moment. Right? Because equivalence says I can do that. I can reduce down to a single force, single moment. Sometimes I can reduce down to one force. Okay? And in the textbook, he does give you samples of what it is to have a pin, a roller. Here's a rocker, same thing as a roller. You see these guys more up north where you get extreme, you get cold, 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 and then in the summer they'll go up to 95 and sometimes 100. So they tend to have this rocker rather than a roller. This is an example of a roller. It's just one object sitting on top of another. That's a roller. Okay? Here you see a pin reaction, and I showed you one that I took a picture of, so you know what it looks like. Okay? We were drawing free body diagrams, because if you can't draw appropriate free body diagrams, you're pretty much cooked in chapter 5 and chapter 6. That's really the bottom line. So we were doing free body diagrams. So let's go back to doing free body diagrams and then start doing some problems. We're going to have an extra pencil. So here we're on page 87. We look at this and we say, all right, I want to draw a free body diagram of this. If I do this, it will be a free body diagram, but it won't be appropriate. Why won't it be appropriate? Well, because I will have touched the cable at A, I will have touched the pin at B, I will have touched the pin at C, at D. That's 2 for each pin, that's 4, and the cable is 5 unknowns. I.e., I only have 3 equations, 5 unknowns, I can't solve this. It will be a free body diagram, but it's useless to you because I can't solve for everything. So the best thing to do would be to come in and create 2 free body diagrams. One that cuts through here, comes around and back. The other that cuts through here and back. That would be a little better, because now I generate how many equations? 6. 3 per free body diagram. That makes life much easier for me. And how many unknowns would I generate? 6. Because you're going to generate this unknown between the 2. So this is sitting like this. So this is pushing down on this member. This member is pushing up on that member. That's a normal force. So my free body diagram of A, B, C will look like this. Cable tension TA. I have a BX, BY, solid member W is equal to 100 pounds, I will have a normal force NC, which is at 2, 3. Please notice in the diagram it says 3 horizontal, 2 vertical. When I draw the NC, it becomes 2 vertical, 3 horizontal, because it's the complementary angle. If I were doing angles, I would have if this was 30 degrees, then I'd have the complement that, which is 60. But the complement of 3, 2 is 2, 3. Free body diagram of the other, which is ECD, looks like this. I'll have a dy dx. I will have a normal force NC here, which is at 2, 3. And I'll have a single force 500 pounds. Now, count the unknowns. 1, 2, 3, 4, 5, 6. There are 6 unknowns, but I also have 6 equations, 3 per free body diagram. That's awesome. Where do you want to start writing equations? ABC or ECD? Where would you want to write right away the equations? I would want to start right here because there's 1, 2, 3 unknowns. How many equations do I have? 3. I will find all 3 of those unknowns. Once I find NC, I'll take its value, take it over there, and I have 1, 2, 3 unknowns there. Again, remember, this is Newton's third law in action.
Should we just switch dx to y?
Huh?
Dy dx.
By, oh, yeah, whatever. This is bx, dy. Yep. Questions? All right, moving down to the bottom one. There's a pin here. Notice, if I draw a free body diagram of this, that's 2 unknowns, go through here, 2 more unknowns and back. That gives me 4 unknowns. 2 at E from the pin, 2 at A from the pin. Not a good look. That gives me 4 unknowns. I can't solve all that. So instead, I'm going to cut through here, cut through here, cut through this, and back. And then I'm going to cut through here, cut through the pin, and back. So literally what I'm doing is I'm taking this pin, squeezing it, pulling it out, and then separating the 2 pieces. So I'll have a free body diagram of ABC, which is this guy, in which case I will have a single force resultant from the distributed load of 1800. This is single force resultant, 300 times 6, that's 1800. Half of 6 is 3 meters, so we'll put 3 meters here, 3 meters there. I'll have a force, AX, AY. Over here at B, because I took out that pin would exert a force, which is BY here, BX there. And then, of course, you have that single force resultant, or single force of 300 newtons. Free body diagram of BDE would look like this. I would have a EY, EX. Here I would have a BX, BY. Again, this right here is Newton's third law in action. that have to be equal but opposite in direction. For every action, there's an equal and opposite reaction. Well, if the reaction here is to the left over here, since it's the same pin, gotta be to the right, this is upward, and that's gotta be downward. This diagram here is huge. Box it in because we're going to come back to it here shortly and say something about it. For now, we'll leave it at that. Now, do I have enough unknowns and enough equations? Well, I have 1, 2, 3, 4, already counted, 5, 6. Do I have 6 equations? Yeah. 3 per free body diagram. I have 6 equations, 6 unknowns. It is solvable. Start writing equations. Does it matter where I start to write equations? The answer is no. Because in each free body diagram I have 1, 2, 3, 4. 1, 2, 3, 4. That doesn't help me. It doesn't matter where you start. In the other one, it was obvious where you should start, where I only have 3 unknowns. Here, it doesn't matter where I start. Start wherever the hell you want. Because you're not going to get everything. You're going to get relationships, and then eventually you're going to have to solve 2 equations with 2 unknowns or something of that nature. Okay? Questions? Moving on. Draw the free body diagram of this one. Well, if I do this, although it's a free body diagram, it ain't appropriate. Why not? Well, I got 2 unknowns at A, 2 unknowns at C. That's 4 unknowns. I only have 3 equations. That sucks. I have a pin at B. So what I'm going to do is I'm going to take this pin out and separate it into 2 pieces. So I'm going to draw a free body diagram that looks like this. 2 free body diagrams, one this way, one that way. So the first free body diagram here of AB will look like this. I've got an AY, an AX, I got 210 external load, I got a BX, and a BY. The other free body diagram that is free body diagram of BC looks like this. I should have BX this way. I should have BY that way. Again, what did I just do? I basically did Newton's third law again. Over here I will have my 300, and then of course I have my CX and CY. Again, do I have number of equations equal number of unknowns? Well, there's 1, 2, 3, 4, counted already, 5, 6. Yup, 6 equations, because I have 3 per free body diagram, and I have 6 unknowns. It is solvable. Questions on that? Now, the one at the top of this looks like this. Notice I have a pin at a roller. It doesn't matter if I have 2 circles or 3 circles or 4 circles. It's just a roller representation. So by doing a free body diagram that looks like this, I can accomplish my goal because, in essence, this is an AY, this is an AX, this is some DY, and I have a weight downward, which is the 260 pounds. So, can I solve for it? Yeah. There's 1, 2, 3 unknowns. let's convolute it just a little bit. I say to you is, yes, I want you to find A, X, A, Y, and D, Y. But I also want you to tell me the pin reaction at B. Well, the pin reaction at B, I can't solve for. Why not? I didn't go through it. My outline went through A, went through D, came around, and I have an external weight. Weight is just an external force. I put it down as W. But I didn't touch B. Therefore, I can't calculate B. So if I ask you to calculate B, the pin reaction right here, you're going to have to do this. You're going to have to come in and cut through here, cut through there, go around, cut through here, and back. You're going to have to cut through here, cut through there, come around, cut through here, and back. So now, I would say my free body diagram of AB should look like this. I should have an AY, AX, but I touched this cable here. I gotta show that T. I have to show here, because I basically took out that, I gotta show a BX and a BY. But I also have to show, this is AB, I still have to show a normal force because this ball is sitting on this side right here and that side right there. So there's got to be a normal force, so I'm going to show here an N2 set. And over here, I'm going to draw a free body diagram of BD. That looks like this. I would have a dy. I'd have a cable tension T because I touched that cable right there. I got to show B. Well, that has to be opposite of what I drew already. And then I have to have an N1. The normal forces are always going to be perpendicular. Where are the normal forces coming from? Well, if I draw a free body diagram of this ball, I will have weight downward 260. Here's this, here's that. I'm going to show a force of N1 here and N2 there. These are perpendicular to those surfaces. So this is the whole shebang dismembered into its pieces. Now understand, these are not A, B, and then B, whatever. It's one solid member, so this is AB right here, this is BC right there, and I'm pinned right in the middle where my two hands cross, or my two arms cross. Okay? It's the same thing as when you have a folding seat. You know those chairs that you kind of fold and put into a bag? So what you have when you have a folding chair that goes into a bag is something that looks like this. And then you have a leg, and then another leg, and what you have here is a pin. That is not one piece, two piece, three piece, four piece. It's one big piece, another big piece. And the reason there's a pin there is because a pin does not allow it to move this way, it doesn't allow it to move that way, but it does not restrict it being turned so you can position it this way to put it in the bag. So it's not restricting any movement. That's why there's a pin there. Because if there was a restriction to movement, you couldn't put it in the bag. So it sits like this, and you turn it so that you can put it in the bag. And that's why there's a pin there. But I want you to understand this is one solid member, one solid member. Same thing as here. This is one solid member, this is another solid member. It's not four pieces that are stuck together. Okay? Now, all I'm doing here is I am foreshadowing what is to come in chapter 6. It is in chapter 6 that we are going to do frames and machines. This is exactly how we're going to tackle a frame problem. We're going to dismember into its pieces. It could be 2 pieces, it could be 3 pieces, it could be 4 pieces, whatever. And for every piece, you're going to have 3 equations of equilibrium to write. So it is essential that you get the idea of drawing free body diagrams correctly starting now. Because what you see in the free body diagram, I'm going to put in the equations. Let's be honest. Okay? Let's start solving some problems. So we already solved this one on page 89. Page 90. Beam problems are the easiest because you cut here, cut there, cut around, and back. And by the way, this is known as a overhanging beam. Because you got this little piece that just is sitting, floating out in air, so to speak. This, where I have the pin and roller at one end and the other end, and it doesn't matter if the pin is on the left or the pin is on the right. This is known as a simply supported beam. And then of course you have what's known as the one that's embedded into the wall. That is the cantilever beam. You have a vocabulary just like lawyers do, just like doctors do. You need to know the vocabulary so you can talk intelligently to somebody. So you're out in the field and say, hey, we need to put a cantilever beam in here. Okay, that in your mind should say, okay, we're embedding a beam in there and it's at the other end it can do this. It's floating by itself and can go up and down freely. All right, so my free body diagram of this is easy. Beams are the easiest. What do I have? I have an AX, an AY, I have 100, I have 200, I have a moment of 500, I have a BY from the roller, I have 300 applied load, and at the very end I have 400. That's my free body diagram. Wherever my circle touched, I got to show. Well, I touched the pin, AXAY. I touched the moment, got to put a moment. I touched the roller, got to put the roller. I touched this 400, got to put the 400. I touched this guy 300. I touched this guy 200, and I came back. Easy. Well, some forces in the x equals 0 positive to the left. AX equals 0. What? Is that legit? Yes. Why? Am I surprised by this? The answer is no. Why not? The answer is beams are not intended to carry axial loads, loads along their axis. That is not the purpose of a beam. Beams are efficient at carrying transverse loads perpendicular to their axis. So that's the function of a beam, to carry loads perpendicular to the axis. So to see AX equals 0, I ain't shocked. You want to carry an axial load, a load along the axis, take the beam, rotate it 90 degrees. What do you got? What do we call that? A column or post. Now, columns do carry loads along their axis. That is their primary function. So a column is nothing more than a beam rotated 90 degrees, and it's done so I can carry a load through the axis of the column. It sucks at carrying loads perpendicular to it, but it's very efficient in carrying axial loads. Okay? Now, if you're doing this problem, what do you think I should do? A moment or some forces in the y? If you're doing this problem on a test, what would you do next? Is what I'm asking. I would do a moment. Where do you want to do a moment? There's really two ideal places to take a moment. What are the ideal places on this problem? Where would you take a moment? At A or at B. Those are the two ideal. Can I take it anywhere? Yes. But if I do it at A, I eliminate all of these guys. If I do it at B, I eliminate, well, AX is 0, so I eliminate these two and I will get AY. Now, I'm going to do the opposite. I'm going to say, fuck you, Nora, I'm going to do it my way. And I'm going to write some force in the Y. Okay, go ahead. I don't care. Some force in the Y equals 0, positive upward. That says AY plus BY minus 100, minus 200, minus 300, minus 400 equals 0. Or AY plus BY is equal to 1,000. So you did it your way, didn't follow what I asked you to do, what I thought would be a better idea, which is, hey, you know what? We should take moments. Why should we take moments? Because usually moments, 8 to 9 out of 10 times, will give you a value. Notice I wrote some force in the Y. Did you get a value? Well, that kind of sucks. I got an equation. I didn't get a value. Okay, you did it your way. Some moments. I want to take some moments at A, clockwise positive, equal to 0. So this is going to be the moment of 500. A moment is a moment, you just dump it in the equation and put in the right sign. I said clockwise. Well, that moment of 500 is clockwise, so I'm going to put a positive on it. Great. Positive it is. Minus BY times 10. Notice this arrow is BY. It goes around A in a counterclockwise fashion, so it's got to have a negative. Next, I have plus 200 times 8. There's the force, that's the distance. Plus 300 times 10. Plus 400 times 15. All must equal 0. Oh, look at that. You wrote a moment equation, what came out right away? BY. That's beautiful. 1110. It's a positive, so I'm a genius. Upward is correct. Again, those values of AX, AY, their directions, you can do whatever the hell you want with them. You want to go downward, great. You want to go upward, great. You want to go to the left, great. You want to go to the right, I don't care. It doesn't matter. The math will tell you if you got the direction right. So I assumed AY upward, BY upward, AX to the left. I could have just said AY downward, BY downward. I could have done whatever. Okay? So now I take this value and I back substitute into here. Well, if I do that, AY is going to come out as minus 110. What the hell's the minus sign telling me? Hey, doofus, you screwed up the direction of AY. It is not upward. It's actually got to be downward. Oh, shit. Does it matter? No, just flip the arrow now. So my final answer is AY is equal to 110 pounds downward. Now think about this. doesn't make any sense. So you're sitting right here, here's this beam, right? My index finger here is the pin. I'm pushing down this way. What's this going to try to do? It's going to try to rotate that way. Correct? So what does this pin got to do in order to keep it there rather than rotate downward? So I got to push down in order to keep it from rotating clockwise. So it kind of makes sense that I should get a minus sign. It should be 110 downward. So if I put this like this, notice it's going to rotate counterclockwise. Now if I put a load here, which is downward, and I try to rotate, notice that pin ain't rotating. Yeah, this end is rotating, but that is staying put. That's the reaction from the pin. Okay? Yeah?
Is that supposed to be 100? How can the first BY equals 1,110, the other one's 110?
Joel, this is 1110. If I bring it over to the other side, it's minus 110.
Yeah, but this.
Sum is 110.
But why,
Negative.
but why is it less though?
Why what?
Why is it?
I don't understand the question, man. What's the question?
Well, how you get 1,010 went down to 110? I don't.
100 plus 200 plus 300 plus 400 is 1,000.
Yeah, I know that.
Okay. If I do all of this math, I'm going to get 1110. If you don't believe me, do the math. If I take this number, dump it in here, solve for AY, I'm going to take 1,000 minus 1110. I'm going to get a minus 110, which is what I said. Yes?
Okay, now I get it.
Okay. Next problem. Next problem's already pre-worked out. This would be a good problem for you to probably close it up and do it on your own, and then check your answers. But notice, I can do this. Go right here, come around, go right here, come around, go through this pin and back. If I were to draw that free body diagram, what happens? For unknowns. I have a 2 at A and 2 at C as unknowns. XY for A, XY for C. That's 4 unknowns. I only have 3 equations. It's a free body diagram, but it sucks. So instead, this is my free body diagram. I'm going to cut through here, cut through there, cut through here, come around, and cut through the cable and back. So now you can see my free body diagram over here. I cut through the pin, CX, CY. I cut through this cable, that's tension. So I have a tension T and a weight downward W, which is 300 times 9.81. If I sum forces here, sum forces in the Y equals 0, positive upward. That's T minus the weight equals 0, or T equals W. That's why you're showing here this cable as W. Then I cut through here, that's 200 times 6, 1,200 newtons, base times height from the distributed load. It's a rectangle, so it's going to act 3 meters here, 3 meters there. And then I cut through this cable, which if you do the geometry is, well, that's 60, that's going to be 60 by alter interior angles. And that's why you see the free body diagram you see. What's the first thing I did right away when I wrote the equation? What equation did I write? I did a moment instantly. Why? Because I know moments usually give me something. And it did. It gave me TBA. Then I did some force X, dumping in TBA for T. Boom, CX comes out. Dumping in for some forces on the Y, I'll get CY. Pretty easy, pretty standard. Go, let's do it. Okay? Yeah. Cut through where? At B? I did cut through C. That's why you see CX, CY. There's nothing separate. I basically said, let me get rid of this pin and cut through this cable. Because once I don't cut through the pin here at A, I don't have extra unknowns. I avoided it. All right, next problem. This problem right here, I will come back to later. It's not the time for it, so we're skipping it for now. Let's go to page 93. Again, if I do this way, sucky. Why? Well, because I have a pin at A, 2 unknowns. I have a pin at B, 2 more unknowns. Total, 4 unknowns. How many equations? 3. Hey, how come you're sitting there? You what's that? You're supposed to be over there. Oh, no, I know. I'm going to come over here, cut through this pin at C, come around and do this. Then I'm going to cut through here, cut through here, cut through there, and back. So I'm going to draw 2 free body diagrams. Free body diagram of AC, which looks like this. I'm going to show an AX, AY. I'm going to show 50 pounds here. And then this is a pin, so I'm going to show my CX, CY. Again, these directions are totally 100% arbitrary. Okay? Then I'm going to draw free body diagram of BC. That's this horizontal member. I'm going to have a BX, BY. I'm going to have a single concentrated load, single force resultant of 1/2 base 6 height 50. That is equal to 150. Where is it acting? Well, it's a triangular load. Again, triangular load, 1/3 from the fat end or 2/3 from the skinny end. So it would be from here to here, 1/3 of 6, or from here to here, 2/3 of 6. 1/3 of 6 is 2, 2/3 of 6 is 4. Now, what is not arbitrary? Reaction at C is no longer arbitrary because now I have to have CX this way, CY that way, by Newton's third law. I can't avoid that. I cannot arbitrarily put CX, CY on member BC. It is dictated by the free body diagram, by Newton's third law. So if I started here and put CX, CY this way, this would now be dictated by Newton's third law as going CX that way and CY that way. Now the question becomes, hey, where do you want to start writing equations? Well, the first thing I look for is, hey, is there a free body diagram with only 3 unknowns? And the answer is, shit, no. What do? Doesn't matter what you do now. You can start at BC, you can start at AC, it's immaterial. If I had, say, just one right here, 1, 2, 3, that's where I would start. Because I can get everything. Here, it doesn't matter. I'm going to start over here at BC. And I'm going to do some moments at C equals 0. Counterclockwise positive. Could I have done a moment at B? Sure. Sure. This is going to be By times 6 minus 150 times 4 equals 0. By is equal to 100 pounds or 100 kilonewtons upward. Oh, I got something. That's good. I'm going to do some forces in the Y equals 0 positive up. Guess what? I'll have By plus Cy minus 150 equals 0. So I'm going to take this 100, dump it in here. Cy will come out 50 kilonewtons upward. Once I have the 50 kilonewtons for Cy, I will then translate it over to here and say that's got to be 50. That's got to be 50 now. And then lastly, I can say some forces in the X equals 0 positive to the right. Cx minus Bx equals 0. Or Cx equals Bx. Don't be shocked if when we get to chapter 6, you end up with a relationship like this. Cx equals Bx. It is going to happen. So don't be alarmed. Oh my God, I didn't get an answer. It's okay. You're going to have to delay your gratification for a little bit. Sometimes that will happen to you where you get a relationship, not a number. Well, now that I have that, I'm going to go over here. Well, guess what? I'm going to do a moment at A. Because if I do a moment at A, what happens? I'll get Cx. Perfect. If I do a moment here, I'm just going to get a relationship between Ax, Ay, and the 50. I don't want that. I want an answer right away. So it behooves me to do some moments at A equals 0, and I'm going to take clockwise positive. That says 50 times 3 minus Cx times 3 plus 50 times 6 equals 0. Voila, Cx comes out, 150. But now I take that back here, which tells me Bx is equal to 150. Because Cx equals Bx. Right? And now I can come in and say, some forces in the Y equals 0, positive up. That says Ay minus 50 equals 0. Ay equals 100. Upwards. Some forces in the X equals 0, positive to the right. Ax minus Cx equals 0, or Ax equals Cx, but Cx is 150, so Ax is 150. And Ax is 150 to the right. This is upwards. Who's not with me? This one. So I see some sort of block attached to 2 rollers. I do know one thing, once I see something on an incline, I'm going to turn the coordinate system around. So here's my free body diagram. And I'm going to isolate this, and I'm going to say, hey, there's a cable tension here, there's a weight here, W, right? And I'm gonna say some forces in the y equals 0, positive upward, t minus w equals 0, t equals w. Free body diagram of the cart. I'm going to show this. I'm going to have an N1 from the roller. I'm going to have an N2 from the roller. I'm going to have G here, and I'm going to put my coordinate system X, Y. I'm going to put in my weight downward, which is straight down. That's 1,000 times 9.81, which is 9,810 newtons. This angle is the angle of the incline, 30 degrees. I also have a tension this way, which is at a distance of 0.5 from G. This T is equal to W because of this. So I'm going to say some forces in the X equals 0, positive this way. T minus 9810 sine 30 equals 0. This has a component in the X and a component in the Y. That T, which equals W, is equal to 4905 newtons. Well, I'm going to do a moment. Some moments about G equals 0. Counterclockwise positive. That's N1 times 2 minus N2 times 2 plus 4905, which is T, times 1.5 minus 0.5, which really gives me the 0.5 must equal 0. Oh, shit. If I divide everything by 2, I'll get N1 minus N2 is equal to minus 1226.25. Whoa, crap. This is where my moment did not give me an answer. Ah, shit, I'm screwed. Here's the point. You took a moment at G, correct? Where should I have taken a moment? The question is, where should I have taken a moment? What?
Maybe the left end of the card.
Maybe I should take a moment which eliminates as many unknowns as possible. Maybe I should take a moment at N1, or maybe N2. If I take a moment at N1, since I already have the tension, I know the weight, I should be able to get N2. And if I take a moment at N1, I should be able to get N2. Moment at N2, I should get the value of N1. So where you take a moment has a bearing on whether the moment gives you a value or not. If you take a moment at a place that does not eliminate unknowns, you're going to get an equation. I took a moment at G. Was that an ideal location for me to do it? Not really. I should have taken it at N1 or N2 to eliminate one of those unknowns. I didn't. I took it at G. Well, by doing that, I ended up with an equation, not a value. So where you take a moment is completely arbitrary. However, there's really good places to take moments, and there's not so good places to take moments. Taking a moment at G is okay, it just wasn't ideal. Because an ideal place to take a moment would be one which gives me a value. Okay? So I did this on purpose so you can see, yeah, I can take it about G, but it gave me an equation, not a value. If I take it at N2, that's known, that's known, I'll get N1. Or if I take it at N1, I'll get N2. But if I take it at G, I have two unknowns. Now I'm going to carry an equation. I did. So now I come in and I write some forces in the y equals 0, perpendicular positive, N1 plus N2 minus 9810 cosine 30 equals 0. So N1 plus N2 is equal to 849, 5.71. Now what you do is you solve two equations into unknowns. So you'll get to the answer. You won't get it as efficiently as you if you had taken the moment at N1 or N2. So solve the two equations simultaneously and you'll get your answer for N1 and N2. N1 comes out as 3634.73. N2 comes out as 4860.98. These are all newtons. Newtons. Who's still with me? Am I getting my point across to you? Best thing you can do for yourself is take a moment right away when you're doing equilibrium of a rigid body. And you want to take a moment which eliminates as many unknowns as possible. That's the key. Okay? You can take a moment anywhere you chose to. However, I chose to take it about G. I didn't get a value. I got an equation, which is fine. There's nothing wrong with that. But usually when I write a moment, I'm looking for a damn answer. I didn't get one. I got an equation. Okay? Next problem.
You read it right, 1.5 minus 1.5.
Yeah, because G is at 1.5, the cable is at 1, so there's a distance between here and here of 0.5.
So once you're at 1.5 minus 1.5.
Because it's 1.5 minus the 1 to give me that distance right there.
It should be minus 1. Yeah, it should be minus 1.
Say what now?
You did 1.5.
Oh, sorry. Yeah. 1 to give me 1.5. You're right. It is 1.5 minus 1. Next problem. Oh, I see Polish. My favorite. Let's go P. Right? Let's go P. So right away I'm going to say P, this is 2P. That is 2P. That's 4P. That's 4P. That's 8P. So right here is 8P. Now if I isolate this right here, I'm going to have a free body diagram that says 800 down, upwards 4P, upwards 2P, upwards P. That is some forces in the Y equals 0, positive up. 4P plus 2P plus P basically must equal to 800, or P is equal to 114.28. So 8 times 114.28, that's going to give me 914.24 newtons. So right here is 914.24 newtons. That's what that's telling me. So as far as I'm concerned, you can throw away the damn pulley system. I don't care anymore about it. I got what I needed, which was the 914.24 going to the L bracket. Now I'm going to come in and I'm going to say, hey, let's do this. Cut through here, cut through there, cut through this cable. And then rather than go through here, that would give me 2 unknowns, 2 more unknowns, 4 unknowns. The hell with it, I'm going to cut through the cable and back. That is the free body diagram I want. I don't want to cut through that pin, and another pin. So now I can just simply write, hey, free body diagram looks like this. I have AY, AX. I have a single force resultant, which is 320 acting 0.4 meters. I have a cable here that's going to the pulleys, 914.28. And I have a cable here, which I'm going to call T. And this angle is theta. Theta, if you look at the geometry, is tangent inverse of 0.24 over 0.18. It's a 3-4-5 triangle. Theta is equal to 53.13 degrees. What's the first thing you want to do? Please tell me. Moment, where? At A. A eliminates AX, AY. I want to take a moment which eliminates as many unknowns as possible. So I'm going to come in and I'm going to say, let's sum moments at A. And I'm going to take counterclockwise positive equals 0. That's going to be T sine of 53.13. That's the force. The distance is 0.18. So this guy right here has a component this way and a component that way. This component goes through the line of action of A. It creates no moment. But this one here, which is the sine 53, does create a moment. Minus 914.24 times 0.18 minus 320 times 0.4, all equals 0. So that's creating a moment, that's creating a moment, and this x component of the t is creating a moment. There they are. Well, guess what? That's one unknown. T comes out 2,031.68 newtons. Love it. That's why I did a moment right away at A, so I can get a value. Last time I was stupid, and I took a moment at G and didn't get a value. I got a relationship between N1 and N2. That was it. Here I was a little smarter and said, let me take a moment at A. That gives me T. Now I just simply say, some forces in the x equals 0, positive to the right, AX plus 914.24 minus 2031.68, that's the T, sine of 53.13 equals 0, AX comes out 711.04 newtons. Then I come in and say, hey, let's do a sum forces in the y equals 0, positive upward. That says AY minus 320 minus 2031.68, that's T, cosine 53.13 equals 0. AY comes out 1539 newtons. Voila. Gotta love it. Gotta love it. Questions? What?
Where does the 340 come from? Up on the left.
Distributed load. What was the distributed load? The distributed load was 400 times 0.8. So 400 times 0.8, that's 320. All right? We're not done yet. Open up the book, because this is important coming at you. I want to go to problem 98, page 98. This is what's known as a propped up beam. It's a cantilever with a roller at the end. Now, I want to find the support reactions. So I'm gonna cut through this fixed support, come around, and back. Well, if I draw this free body diagram, this is what I have. I have an AY, I have an AX, I have a moment A, I have a single concentrated load here of 100 acting at the middle, I have a BY, and I have a force of 50. Good free body diagram? There's too many unknowns. It's the only free body diagram I can draw though. Oh shit. There's no other free body diagram I can draw to make this better for me. Yes, there are 4 unknowns. 1, 2, 3, 4. I can't solve that. I can't do a free body diagram that say, let's go through here, here, and back. Because now I'm cutting through the beam. Now I've got internal forces. I don't want to calculate internal forces. If I did, then I'd cut through the beam. I'm kind of stuck. This is the type of problem we cannot teach you in this class. This is what's known as a statically indeterminate problem. In other words, from statics alone, I can't solve this problem. That is why you have to go to the next class, EML 3200, EGM 3331, Mechanics of Solids or Mechanics of Materials. That's where they will teach you how to solve statically indeterminate problems for the first time. And the real world is a lot of statically indeterminate problems. I can't teach you this yet. Why can't I teach? Because in order for me to solve this one, I have to go to deflection. How does this beam deflect under the load? Well, our model of reality is rigid body. There is no deflection. There's no change in shape or size or anything. So I can't teach you this. But you can see what you have because I can say some forces in the x equals 0. Positive to the right, that says AX minus 50 equals 0, AX equals 50. So, from statically indeterminate, I can never solve for the support. No, I can't solve. I just can't solve for all of them. I just solve for one of them. If I write the equations, guess what? Some forces in the y equals 0 positive upward. That says AY plus BY must equal to 100. Great, but that's 2 unknowns. And if I do a sum moments at A equals 0, counterclockwise positive, that says BY times 10 minus 100 times 5 plus the MA equals 0. Well, I have 2 equations, but I have at the same time AY, BY, and MA. 2 equations, 3 unknowns, I can't solve them. That's why we classify this as a statically indeterminate problem. So here comes 4 definitions for you. 1, statically determinate. That's all the problems we do in this class. Number of unknowns equals number of equations of equilibrium. 2, statically indeterminate. Number of unknowns greater than number of equations of equilibrium. 3, partially constrained. This is fewer unknowns than equations of equilibrium. Example of this would be something like this. That is partially constrained. Because yes, I'm constraining the y's, because I got two rollers, but I ain't constraining the x. So this thing is going to move in the x direction. So if I want to make it so it doesn't move, I need another, say, roller right here. Now this roller supplies a 100 the other way, and it won't move. But if I just leave it like this, that's partially constrained. Number 4, improperly constrained. This says number of unknowns equals number of equations of equilibrium. But, there's the big but, one equation gives no info. And we make a big note here. Improperly constrained usually means, implies, reactions are either parallel or concurrent. Example. I have number of equations, 3, number of unknowns, 3, rollers, great. But if I were to write some force in the x, what happens? 100 equals 0, that's no information. You get shitty information. I will see you tomorrow for the test. That's the dungeon.